Good day. I'm Norman Wildberger, and today we're going to talk about applications of the idea of vector that we introduced in our last video. A parallelogram is a particular type of quadrilateral, meaning that there are 4 points in the plane, and no 3 of these points should be on a line. Our official definition could be expressed this way, that A1, A2, A3, A4 is a parallelogram. It means that the vector A1, A2 is equal to the vector A4, A3. So we require that this vector from here to here is equal to this vector from here to here. And that turns out to be equivalent to the other opposite vectors being equal. A2, A3 equals A1, A4. In other words, this vector here equals this vector here. In this particular example, here are what the numbers look like. The vector A1, A2 is 1, 3 because we go over 1 and up 3 going from A1 to A2. That's the same as going from A4 to A3, over 1 and up 3. The vector A1, A4 is over 5 and up 1. That's the same as the vector A2, A3, over 5 and up 1. And I remind you that we use round brackets for vectors to distinguish them from points, which are expressed with square brackets. The vector notation allows us to do arithmetic with vectors. For example, we can combine vectors to form new vectors. The vector A1, A3, which is a diagonal of this parallelogram, is a combination of A1, A2 and A2, A3. So arithmetically, there's the vector A1, A2, there's the vector A2, A3. To combine them or add them, we just add them component-wise. The 1 plus 5 gives us 6, the 3 plus 1 gives us 4. And indeed, we can check that going from here to here involves going over 6 and going up 4. So this is indeed the vector 6, 4. In a similar kind of way, if we wanted to describe the other diagonal, say the vector A2, A4, then that could be expressed as this vector plus this vector. Now this vector A2, A3 is 5, 1, while the vector A3, A4 is a little bit different from A4, A3 because it's going in the opposite direction. So it's negative of this one. So we have to take 5, 1 and we have to subtract 1, 3 to get 4 minus 2. That's the vector A2, A4. And it's an interesting property and a fundamental property of a parallelogram that the two diagonals that we've just found actually bisect each other when they meet. In other words, at that intersection point, let's call it D, this vector is equal to this vector and this vector equals this vector. Up to now, we've talked about lines in terms of their equations. So here's a picture of a line, that line L, in the Cartesian plane with coordinates x here along here and y along here. And this line, for example, goes to the point 2, 0, 3, 2, 4, 4, 5, 6, also 1 minus 2. And its equation is 2x minus y minus 4 equals 0, which we encode in the triple of coefficients. So we say that the line L is the proportion 2 to minus 1 to minus 4. Now the vector language gives us another important way of describing this same line. Namely, the idea is we can describe that line by 2 pieces of information. The first is a point that lies on the line. And that point can be any point. Let's call it A. And the second piece of information is a vector which specifies the direction of that line. So that vector could be any vector which is in the direction of the line. And I've chosen this little vector v here, which is over 1 and up 2. So the vector 1, 2. So in terms of the point and the vector, we can say that the line L is of the form a plus lambda v. In other words, it's all those points that are obtained by starting with A and adding some arbitrary multiple of v. For example, if A was the point 3, 2, then we could express the same line as 3, 2 plus lambda 1, 2. So we start at 3, 2, and we're allowed to add any multiple of the vector 1, 2, and that gives us, as lambda varies, all possible points lying on the line. And not just points in that direction, but also points in that direction, because lambda is also allowed to be negative. Another very useful aspect of vectors is to be able to introduce affine combinations of points. Here's an example of a line going through the point A with coordinates 1, 6, and B with coordinates 5, 2. Suppose we were interested in the midpoint of that segment. In other words, the point C, which lies exactly halfway between A and B. Well, it's pretty clear that what we need to do is we need to take the x coordinate, which is halfway between 1 and 5, namely 3, and the y coordinate, which is halfway between 6 and 2, namely 4. And that is indeed the way to get the midpoint. Another way of thinking about that is to introduce the vector v that goes from A to B. The vector v is obtained by taking the difference between the coordinates here and the coordinates here. 5 minus 1 is 4, and 2 minus 6 is minus 4. That's the vector joining A to B. Now, if we're interested in the midpoint here, what we can do is we can start at A, and we can add half of that vector v. Okay, half the way to B. So half of v will be the vector 2 minus 2. And so another way of obtaining this midpoint C is to start at A and to add half of v. So we take the point A, which is 1, 6, and we add this half of v, 2 minus 2. And if you add this and this, you get 3, 4. That's a useful way of thinking because it allows for generalization. We can describe any point on this line as a combination of the point A and a multiple of this direction vector v. V is the vector AB. So an arbitrary point of the form A plus lambda AB can be symbolically written in the following way. We can write A plus lambda. The vector AB was obtained arithmetically by taking the difference between the coordinates of B and A. And if we combine these two things, there's an A here minus lambda A for a total of 1 minus lambda A and lambda B. This is called an affine combination of the points A and B, and it represents a point lying on the line AB. When lambda is equal to a half, we get what we call the midpoint. But we can also consider other combinations. For example, this point D is A plus 3/4 of the vector V. And so when we write it in terms of A and B, we get 1/4 A plus 3/4 B, meaning that it's intuitively it's a weighting of the points A and B, 1/4 weighting to A, 3/4 weighting to B, and since 3/4 is bigger than 1/4, we get something that's closer to B, but still on the line AB. So this is a new way of describing points lying on a line as a combination of A and B, where the two coefficients always add up to 1. So those are some interesting applications of vectors, which are very useful objects for geometry. Now that we've done a fair amount of elementary geometry, it's time to survey and review what exactly are the important conclusions to be drawn for public school education, which is one of our main interests in this series. So next time we're going to address some of those issues. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.